Okay. Okay. As I mentioned, rational expectations from an income hypothesis, straightforward. Uh, you take your income over your lifetime and you smooth it. If you earn a little as a student, then later on you earn more, where you'll be able to smooth that consumption. You'll borrow now, right, and you pay back that money when you earn more later. And that's just a permanent income, their permanent income hypothesis. You rationally estimate your income over your lifetime, and then you smooth your consumption given that lifetime consumption. And we talked about last week, we said your permanent income is simply the sum of all your income over each period. So each period you earn some income, your permanent income will simply be the sum of all that income you earn each period. And any shock to that income will be smooth over. If you have a shock and you expect it to be a one-time shock, let's say you break your leg and aren't able to work that period, well, you know that that's not going to be something that's permanent. So you'll smooth your consumption. You'll excuse me. You'll increase your marginal propensity to consume that one period. You'll earn part of your income. Maybe you'll borrow that period, and then later on, when your leg heals and you're able to work again, no period to work a little less to pay back the loan that you did when your leg is broken. As I said, the idea behind rational expectation is then to propose that in forming their expectations of likely future income streams, individuals use information about actual income they experience. More particularly, propose that individuals are not systematically biased. What that means is that if you keep making errors in your estimate of your income, you'll be rational and you'll adjust. If I keep overestimating my income, well then I know that for some reason I'm overestimating my income. I'll adjust and I'll lower my income. Vice versa, if I'm underestimating my income, I'll adjust, increase my estimates of my permanent income. It's analogous, excuse me, to the microeconomic model of consumers maximizing utility, right? We don't propose that every time a consumer goes to the store, he looks at the relative prices of different baskets of goods, in this case A and B, then he asks himself what his utility function does relative to Lagrangian, make a few calculations at the store, and decide what he's going to buy. Well, obviously, nobody does that. Rather, the idea of utility maximization is a way of modeling the consumer as having a well-defined set of goals, like we talked about in micro, and reacting intelligently to his environment. He'll experiment by varying consumption away from current levels and then change. And if the change makes him worse off, well, he goes back the other way. If it makes him better off, he continues to use. So the system has a feedback mechanism, and by reacting to that feedback mechanism, the consumer can alter his choices until they maximize his utility. Similarly, we can postulate that individuals will avoid having biased expectations if they can. In other words, they're not going to have any systematic errors. From this, it follows that economists can get an accurate model of an actual statistical process followed by income. An a priori prediction, we shall also have an accurate model of individual expectations. Note, this doesn't mean that we assume that individuals know the model or know how the model is generated, simply that they're acting in action. So we build a model of their choice behavior just like we did in micro, but over time. We can think of a good model of behavior of economic variables relative to individual choices. We can think the individual has an unbiased expectation. Then our model ought also to provide a model of individual expectations. So here's our first one. By the way, we're gonna be using eigenvalues and eigenroots in this lecture. I don't expect you guys to use them for the test. I just expect you to have a general understanding of them. I've noticed that the matrix algebra, some of you have a little bit of trouble with. Basically, so the eigenvalues and eigenroots, I just want you to know that have a general understanding, but you're not going to be tested. You're not going to be asked to calculate an eigenvalue and eigenroot. Let's go on. Suppose I have a random variable for income that's normally distributed with mean y bar and variance sigma squared y. I'm going to assume that the y's aren't autocorrelated with each other, i.e. the covariance between y in one period, yt, and y in another period, yf, is 0. Of course, where s not equal to t. In other words, that we're just going to assume that's going to mean that we're not going to have any autocorrelation if we address yt on like values itself. Or to begin with, later on we'll write that assumption. There's a good model of income, or the income process that individual faces, then we should expect a good model of expectations to be the mean of the random variable, y bar. In this case, that has the expected value of yt plus I is y bar for, excuse me, y bar for any I greater than 1, greater than or equal to 1, and of course yt for I equal to 0. And that just means that this period I know what my income is, so I don't have to guess. So his permanent income would be then given by that equation that we talked about, except that now we're going to introduce, instead of the yt, we're going to have y bar, the average of all. So the permanent income would be 1 minus beta yt, because we know yt, plus 1 minus beta, the summation of beta to the I power y bar, where I bar is essentially our expectation for y in future periods. So taking the summation out of the mean, so we'll end up with 1 minus beta yt plus beta y bar. So our permanent income will be a weighted average of current income and the normal mean income, y bar, with weights of a function of the discount factor beta. So in this case, consumption would be, and remember K was just the proportional or the proportion of income that we consume. So consumption, CT would be K times YPT, where YPT is our permanent income, and KT plus UT, where UT is in there. And we're going to see later on that UT is going to have mean 0 and VIIT. So I can write that for the end, our permanent income for our permanent income for YPT. We had the equation last. So we get K beta y bar plus K 1 minus beta yt plus UT. And I can rewrite that as follows. K y bar plus K 1 minus beta yt minus y bar plus UT. So the mean income can be thought of our usual income, like y bar. Current consumption is the marginal propensity to consume out of wealth. K times y bar. Remember, K is just that marginal propensity to consume, or the proportion of income that we actually consume, plus the fraction 1 minus beta of current deviations of income, yt from y bar. Observe that the effects of yt on ct depend on beta, and hence the time period, which reflects the fact that the information revealed by the assumption that yt and ys are independent also depends on the time period. T can't be s. Okay, so now let's think of like econometricians, right? Observing the consumer. So we estimate y bar, sigma squared y, the variance of y. Uh, the intercept, k beta y bar, and the slope, k times 1 minus beta. So I can recover k and beta and compare those with the estimate from other sources. In other words, I can test the model. Right? Also, the theory of the distribution of y is correct. The residuals of the estimated consumption function should be uncorrelated over time. Okay. We do not expect this model to do very well on real data since yt minus y bar in practice would actually be autocorrelated. We made the assumption that yt wasn't correlated with ys, but we know that's a bad assumption. Current income would thus give the consumer some information about his likely future income and cause him to revise his estimate of expected future income. Why? Because you know it's autocorrelated. In other words, there is some information in past income. So, if we do have autocorrelated income, let's take our model and instead of beta, let's use rho, correlation coefficient. So yt 1 minus rho, y bar plus rho, yt minus 1 plus an error term, epsilon, where rho is between 0 and 1, and epsilon is normally distributed with mean y bar and variance sigma squared y. Then I can take the difference between income today and my average income and calculate it, and that'll be rho yt minus 1 y bar plus epsilon. Right? And I can write what's in here as follows. Yt minus y bar is going to be some function of rho I, yt minus I minus yt plus I minus y bar, right? Is going to equal rho I yt minus y bar plus some linear combination of our past error terms, our past epsilon, right? And that's where our autocorrelation comes in, depending on how far I go into the future. So taking our expectations, therefore, with this autocorrelation, my expectation for my future income, yt plus I, is going to be y bar plus rho I, yt minus y bar for every I greater than 0. And of course, just like before, we know what our income is today. We don't have to guess, so it's just yt for I equals 0. Okay. So I substitute the equation we had before. By the way, this is, I have an equation 6 here. This is in your notes, so you get it down with equation. So our permanent income now is going to be 1 minus beta yt equals 1 minus beta times the summation of beta I, y bar, rho I to the yt minus y bar. This comes from the equation we just had. I can rewrite that as 1 minus beta yt times beta y bar plus 1 minus beta yt minus y bar times summation of beta I rho I. Taking my y's outside. And I can rewrite that, right, as follows. Beta 1 minus rho divided by 1 minus beta rho y bar plus 1 minus beta rho yt. Now notice that now we have something that we can estimate. We can estimate these coefficients. Okay. Going over to the consumption function, we have the coefficients like we did before, but a little more complicated. So our consumption function is linear yt, but the interpretations of coefficient are going to be different than before. So I have ct equals k beta 1 minus rho divided by 1 minus rho, 1 minus rho beta times y bar plus k 1 minus beta over 1 minus beta rho yt plus ut. So I compare this with our consumption function before, right? Since 1 minus beta rho is greater than 1 minus rho, and that's because we're assuming that both beta and rho are less than 1. So I'm multiplying those two, right? So 1 minus beta rho is greater than 1 minus rho. With the autocorrelation income, the amount consumed out of current income is higher, right? We have shocks. Higher current income now leads to consumers expect higher future income, right? This is in line with our adaptive expectation. To expect higher future income because of autocorrelation, hence the consumer tends to consume a greater proportion of current income, YT. Also, if rho goes to 0, the consumption function, in other words, as autocorrelation decreases, the consumption function in example 2 reduces to the function in example 1. The same thing. Our autocorrelation goes to 0, they're the same thing. Also note that as autocorrelation gets big, when rho goes to 1, the propensity to consume out of current income, YT goes to K. Okay, sorry. Okay. ¿Tenía pregunta, Gisela? ¿Ah? Esa es la proporción de ingresos que tú consumes. Por ejemplo, si tú consumes un 90% de tu ingreso, cada va a ser controlado. Okay. So note that the connotation could recover the estimates, as I told you, of all the parameters, beta, rho, and everything else that we need. All he has to do is first regress yt on the constant in yt minus 1, and get his estimates of rho and y bar. Right? And then regress ct on the constant and yt to get estimates of the slope and intercept of the consumption function. From which estimates of k, beta, can be recovered using the estimates of y bar and rho found in 1. The first step. So if you assume all those estimates are right, and the model's good, those two steps will get you everything you need. So here we get just one estimate of each parameter. What that means is the model's not over-identified. Right? The estimated consumption function just gives us two equations to solve the two parameters, same data. And if you remember from your econometrics class, if you have more variables than you have equations, you say your model is over-identified. In this case, it's not. So, what we do, we can use the over-identifying restrictions to get another test of our theory. If the theory is correct, the different estimates of the parameters we can derive from the regression coefficient should be consistent with one another. That's not always true. A lot of times you get estimates that just aren't realistic. One estimate will be fine, the other estimate will be imaginary or just something that couldn't possibly happen. Okay, so we haven't talked about variance so far. But we saw that it was important before when we were talking about estimates of our models and how they were affected by different parameters. For example, interest rates, monetary policy, whatever it might be, or fiscal policy. It was important for explaining the cross-sectional evidence examined by Friedman and for if it's only the different time series estimates of the consumption function. So we introduce variances to analysis, but supposing the consumer is somewhat observed. In other words, those estimates of his future income aren't 100%. So there's going to be some variance, and therefore some signaling process. And that signaling process, of course, right? I'm going to school. That's my signal. I'm going to get, when I graduate, I'm going to get more money. That can be a signal. It can also be, I got a raise, my permanent income is increased. That signal is a little more certain, but that's also a signal. Anything that gives you evidence that your income is going to change in the future is a signal. So you consider a set of random variables, y, x1 through xn, and they all have population means uy, u1 through un, which are finite, and all have finite second moments, the means are finite. Therefore, I can say that the expected value of y squared is equal to the expected, is equal to sigma squared y, the expected value of x1 squared is equal to sigma squared 1, the expected value of x2 squared is equal to sigma squared 2, and so on. What does this mean? What does it mean about, what does it mean for the average? Well, which has something about it. If you just remember the formula for variance, and you'll see it. Basically, if the expected value of y squared is equal to the variance, you expect the mean to be 0. Then it can be shown, for those of you who know some analysis using the Cauchy-Schwarz inequality, k times y is less than or equal to x times y. Shorten that all the second moments, the expected value of xj, xy, the expected value of yxi exists and are finite. That's all. You probably didn't see this in your linear algebra class. You might have seen it in the economics class. Nope. That's okay. It's not that important. It's just math. So I mean, if you're really curious, you can look it up. It's not that difficult, and the proof is not overly difficult, not super simple, but it's something I think anybody had a linear algebra class. Okay. Now consider y on the basis of known values of the random variable xi and the first and second moments of all the random variables in the set. More specifically, we should look at the best linear estimates of y. That is, our estimate of y hat, is equal to some function of all the x's. In this case, a linear combination. And of course, since we're doing the econometric, we want to minimize, right, the difference between our estimate and the actual ones. So we're going to go through and quickly review a little bit of econometrics. We want, in other words, we want our results to be orthogonal, right? So the necessary switch condition for all the coefficients, a0 through an, to minimize basically the following function. With this, of course, is y hat we just talked about. I want to minimize that. So the expected value of y minus a0 plus a1 x1 all through to xn an times xi is 0 for all i's from one to n. I'm sorry, from 0 to n. In other words, that's all it's saying is that y minus y hat is orthogonal to each xi. Basically, what that does is it means that there's no correlation between independent variables. So here's a proof. Suppose I have a variable J, which is equal to the expected value of Y, minus the summation of all our coefficients times the variables, x1, x2 times, so a1 times x1, a2 times x2, and so on. So I differentiate J with respect to each AI, excuse me. So the partial of J with respect to AK is equal to 2 times the expectation of Y minus the summation of AI xi times xk. I'm sorry. Aquí no es la misma caja que estamos hablando ahorita. Esta caja solamente es uno de los variables. Tenemos x1 hasta xn, ¿no? Xc es uno de esos, cualquiera. So I want that equal to 0 for a minimum for each k. My k is 0 to 10. For which I conclude the orthogonal, orthogonally. Why can't I say that? Anyway, the orthogonal. So, which is the expected value of Y minus the summation of x from AI, xi from I to n times xk is equal to 0 for all k's. So to check the second order for the minimum use vector notation, I have the vector x, which is basically a vector of all the x's x0. I have a vector of my a's, of my coefficients, a0 to an, and I can also write a vector of my y's, and write this in matrix form. The expected value of x prime or x transpose y is equal to the expected value of x prime x times a. And that's just part of orthogonal. I'm sorry? Orthogonality. Thank you. I don't know why I couldn't say that. Anyway, that's part of our orthogonality principle. But the variance covariance matrix x prime x is non-negative definite, so J is minimized by choosing A, coefficient matrix, to satisfy the first order condition in 14. So our summations of XIAIs are called a projection of Y onto, usually call that X space or Euclidean space. So we have 1, x1, x2 to xn. We just project our Y onto our X space. And I can denote that as Py and our constant 1, x1 to xn. So if Y and each of the xi's are normal random variables, then the conditional distribution of Y given the xi's is normal with mean given by the projection. That is, the normal random variables of the projection is also the conditional expectations of Y given the variables xi. And the author denotes, excuse me, tells you to see the text by Rao, but pretty much any advanced econometrics text will show you this. If you guys, I think you guys are using green with Cal, or no books. Okay. Uh, well, maybe he has it in the notes. Okay. So I put epsilon equaling y minus the summation of ai xi, right, as our forecast error. 14, our orthogonality principle and the projection of y onto x space gives us the following. It gives us that the expectation of epsilon xi is going to be 0 for all odds. Right? So that summation, the expected value of epsilon times the summation of all the xi's ai is also going to equal 0. In other words, the expected value of our error is going to be 0, and I can't predict what the errors are a priori from this model, otherwise it's not orthogonal. Okay. Also, the expected value of y squared is going to be the expected value of xiai plus f1 squared. Questions? So, again, you're not going to be tested on that. That's econometrics. Just put that the review. So we can go on. How do we apply this to the signaling process? Well, suppose we have a random variable x, right, that's made up of two components. S, which is a signal, and N, which is noise. If it's something random, something you can't predict, it's not going to affect your permanent and we observe, right, that the expected value of S times N is equal to 0. The expected value of S squared and N squared are finite. And that the expected value of S and N are both 0. Then our best linear forecast of the signal, given the observation, that the expected value of S is equal to A0 plus A1 times X. So put in matrix form, and writing our S equal to A0 plus A1X plus epsilon, multiplying through by 1 and X, taking expectations, to get this in matrix form, where the expected value, the vector, the expected value of X, and the expected value of Sx is equal to a 2 by 2 matrix. I have 1, the expected value of X, the expected value of X on the cross diagonal, and the expected value of X squared on the bottom right hand corner times a coefficient vector A0, A1. But we know that the expected value of the signal by assumption is 0, and therefore the expected value of X is going to be 0. So I can plug those in, and I get the following matrix, which is much easier to solve. I can solve for A0 equaling 0, and therefore A1 is equal to the expected value of X, S times X over the expected value of X squared, which I can rewrite, plugging in for X. The expected value of S times the expected value of S plus N. Of course, the expected value of Sn, we know, so it's just the expected value of S squared. The expected value of Sn is 0. And of course, we can take the expectations through here because the expected value of Sn is 0. So the expected value of S squared plus N plus the expected value of N squared. They can do that. Noting that the expected value of S times N is 0. Therefore, 2 times S times N is also 0. Since the means of S and N are 0, there's no constant term in the forecast for that. If the variance of the noise goes to 0, movements in X completely reveal S. If there's no noise, well, it's also 0. So the coefficient of X is 1. If the variance of S goes to zero, move into next will tell us nothing about X. We can't figure out the signal. And the coefficient of X is zero, on X is zero. Okay. Questions? Okay. So let's take that signaling process and put it with our autoregressive model that we had before. So now suppose that yt is equal to y bar plus some error term vt plus another error term yt that was stated before, where ut is IID standard normal, independent of all the v's. That means all the v's, leads or lags. But vt is equal to rho vt minus 1, it's autocorrelated with itself, plus some term w, where w is IID standard normal. So I assume individuals know current and all path levels of y, but do not know the decomposition of y. The decomposition of y onto u or v in any period. So to model the permanent income, we do something similar to before. In our first equation. Right? So I need to determine the expected value of yt plus I, my future income. When yt is given by the process described above, first I have to figure out what the expected value of yt is, and I know for this period it's just but for future, the expected value of yt plus I is equal to y bar, the average y, plus the expected value of vt plus I. That's our autocorrelated error term, or the part of our error term that's autocorrelated. If we thought of basically v plus u being our error term, and then splitting it up into a non-correlated part and the autocorrelated part. Okay. So the expected value of vt plus I is going to be rho I times the expected value of vt. Right? Substituting that into our permanent income, our permanent income equation, and the equation before for vt. Put it in here, and our equation for permanent income, I get 1 minus beta yt plus 1 minus beta times the summation of b to the I power y bar plus rho y, the expected value of bt at time t. So rewriting that, I get 1 minus beta yt plus beta y bar plus 1 minus beta rho over 1 minus beta rho times the expected value of vt at time t. Again, we're getting something similar to what we had before, except 1 minus beta rho right before the time of so now observe that from before that our vt is equal to rho vt minus 1 plus w. So that the expected value of vt is rho expected value of vt minus 1 plus the expected value of w. However, consumers will learn nothing new about t at t minus 1, since it depends on the shocks from t minus 1 and earlier. Hence, the expected value of vt minus 1 is equal to the expected value of vt minus 1 last period. So our expected value of vt minus 1 this period is equal to our expected value of vt minus 1 last period. However, hence, we can conclude that 1 minus rho times the lagged operator times the expected value of B of BT at time t is simply equal to our expected value of W at time t. So using our singling process that we talked about earlier, I can write yt minus I minus rho yt minus I minus 1. Those I can go back and just take the difference between two time periods in the past, right, for our income. Minus 1 minus rho y bar, our average income. That's going to be equal to Wt minus I plus Ut minus I minus rho yt minus I minus 1. I'm sorry, that's a rho U. So it's equal to Wt minus I plus Ut minus I minus rho Ut minus I minus 1. For all i's greater than or equal to 0. So to obtain Wt, therefore, I can take the summation of our coefficient alpha I times yt minus I plus ut minus I minus rho times ut minus I minus 1 plus epsilon t to get our W's, which is that error term for our B. Well, not an error. Something that acknowledges some function of our B. Where B is function W. So, in this case, our error term epsilon is a forecast error orthogonal to all the terms in the information set. So now I'm multiplying through each term on the right-hand side of 34 and take the expectation to obtain the variance of W. So I get sigma squared W is equal to alpha 0 times sigma squared W plus 1 minus rho squared times sigma squared U plus alpha 1 rho sigma squared U. Okay. The next equation, set equals 0, I get minus alpha I minus 1 rho sigma squared U times alpha 1 sigma squared W plus 1 plus rho squared all times sigma squared U minus alpha I plus 1 sigma squared U. That one it's a little more complicated, but it's basically the same logic as before, just a little more. Okay. So equations 36 are a set of difference equations under the convection coefficients alpha I. The complementary equation corresponding to the last equation 36 is as follows: lambda squared rho sigma squared U plus lambda sigma squared W plus 1 minus rho squared sigma squared U plus rho sigma squared U. As I told you, I'm not going to hold you guys accountable for doing roots or eigenvalues. If you don't understand where the lambdas came from, like I said, don't worry about it. Just understand the basic concept. Okay. So I divide that 37 through sigma squared U, and R is going to be the variance. I'm sorry, the ratio of our variance is sigma squared W over sigma squared U. So rho lambda squared minus lambda R, where R is our ratio of variances. 1 plus rho squared plus rho equals 0. So the roots, calculating the lambda, you get the following. We're solving for the lambdas. Those both roots are going to be real, not imaginary. We can write the quadratic equation of the last equation as sigma squared, I'm sorry, lambda squared plus k lambda, again the a different K. This is, I keep forgetting that P doesn't work with this. Where K, K is just all of that other stuff that we calculate in the quadratic. Plus 1 equals 0 for any positive K. Okay. So hence, if our roots are negative, sigma squared K lambda plus 1 is greater than 0, so both roots must be positive. Finally, since the coefficient of lambda squared is 1 and the constant term is 1, the product of the root is therefore 1. Therefore, when you write the two roots as lambda, as 1 over lambda, where lambda is less than 1, I can prove that alpha I is going to equal A lambda I plus B 1 over lambda I for two constants, A and B. But then we must have B equal to 0 if we're going to have a minimum forecast error variance. Essentially, we have a transversality condition for the variance minimization problem. Constant A will determine from the first equation in 35 using the variance, that should be variance ratio R. So it can be written as R is equal to alpha 0, R plus 1 minus rho squared minus alpha 1 rho, which from the previous equation we can write as A, R plus 1 plus rho squared minus alpha rho lambda. So hence, using lambda 2 is equal to 1 minus lambda 1, the first term, plus the square root of the discriminant, I get A is equal to R, remember R is just the ratio of our variances, over R plus 1 plus rho squared plus rho lambda, and that's just going to equal R times lambda, and we can prove that the expected value, which is the 3150, the expected value of WT is going to equal the ratio of our variances, that we reviewed, times the summation of lambda I plus 1, W2 minus 1, plus U2 minus 1, plus rho U2, U2 minus I, plus rho U2 minus I minus 1, equaling R lambda divided by 1 lambda over L, times 1 minus rho times the right operator, Y2 minus 1 minus rho, Y bar. I substitute that in to 31, and I get a permanent income, something very similar to before, except now I have the ratio of variances along with the coefficients and our roots. So to get this, I'd actually have to calculate our roots, but first, it's not that important, just the concept. So I get our permanent income is 1 minus beta Y2 plus beta Y bar, plus 1 minus beta rho, R times lambda, divided by 1 minus beta rho, divided by 1 minus lambda times the right operator, all times what we had before, 1 minus rho times the right operator, Y2, minus 1 minus rho Y bar. If you zoned out from there, that's fine. Like I said, I don't expect you guys to understand the outline. At some point, you guys probably understand it, but I would do that. But for now, it's not necessary. Just that we needed them to get the permanent in my office under those assumptions. Okay. Next thing I want to talk about is something known as random walk, and this is why I finished the lecture last week with that supplemental lecture, just to give you an idea of what a random walk is. Right? So the idea of using the signaling process, mu, showed that adaptive expectations can be equivalent to rational expectations. Right? The basic idea is that the consumer wants to forecast the signal permanent income on the basis of observation of actual income, which is permanent income plus noise. The analysis is essentially identical to the one above in the auto regression case. Both analyses together show that some form of adaptive expectation can be rational under a wide range of circumstances. So, if you take income and you write it as follows, so yt is equal to alpha plus bt plus vt, with ut and wt, and wt, both are going to be independent variables, and wt is going to be equal to the difference between vt and vt minus 1. And we're assuming that both are uncorrelated, even though the VTs can be correlated. So UT and WT are standard normal, with variance for U is sigma for U and variance for W is sigma for W. So the shock, VT, we're going to assume is a random walk, which is like the regression before. Basically, a random walk means that our expected value of VT is what it was before, unless it's a random walk with a trend. Then it's what it was before plus a trend. That's all the time. The key feature of the random walk is there's no tendency for the variable to return to a particular level. Just our best guess is what it was before. So it's not mean reverting, so that if the last thing was above the mean, we don't necessarily expect it to go back. We shall assume that alpha and the variance of U and W are known to the consumer, assuming that alpha is known is equivalent to assuming that forecasts of income aren't biased. The mean of income should be known, and assuming that the variances are known is a way of modeling the assumptions. Okay. So our assumptions, the consumer believes his income will vary from period to period, and the consumer has some idea that shocks have implications for long-term earnings, and tend to have one magnitude given by the standard deviation of W, while those that are the result of a temporary or good or bad luck, the last one period will have a different magnitude. In other words, if I think it's permanent, it's going to affect my consumption more. If I think it's temporary, well, it's not going to affect my consumption a lot. This splits into two shocks. So undoubtedly, the splitting this into two shocks is a simplification, but might be close enough to yield a satisfactory explanation of the behavior. So the model of permanent income, right? Just like before, in the first equation, I need to determine the expected value of yt plus I, where yt is given by the process described above. So expected value of yt plus I is going to equal to alpha plus the expected value of vt plus I plus vt plus I. I separate those out. The expected value of ut plus I is 0, so I get alpha plus the expected value of vt plus I. Since ut is serially uncorrelated, also we can write that vt plus I is going to equal vt plus I minus vt plus I minus 1 plus vt plus I minus 1 plus minus vt plus I minus 2 and so forth, all the way back to vt plus 1 minus vt and vt. Or starting point, and the expected value of W, T plus I minus J is equal to 0 for any J less than I greater than 0, since WT is serially uncorrelated. So therefore, the expected value of VT plus I is just VT. But the expected value of YT plus I is the expected value of Vt plus alpha for any I greater than 1. So basically, I have the same thing. I did all that just to change this from VT minus I to VT. Okay. So the random walk V is like the permanent part of the shock to income, so that the forecast future income and the consumer needs to estimate B. Of course, the current income is also part of permanent income, but it is observed at time t. That is, if I equals 0, the expected value of yt plus I is simply yt. So in this case, of random walking, my guess for income is basically what it was last year, and that's a gap. Okay, questions? All right. So either I'm getting old or just been too long since the strike. I've been tired of standing up. Anyway, used to assume the consumer didn't observe the random walk or the noise part view of income. Rather, he had to form expectations for current values of V, given that his past observations of actual income Y. Actual past incomes are noisy signals of the shock of interest to the consumers. The shock U have no intrinsic value for forecasting future income. They affect the consumer only because they can be confused with shocks W to permanent income. Thus, I wish to calculate VT, right, or the expected value of VT as a function of all past income. So, taking our signaling process, right, and using the orthogonality principle, I have to look at it and sound it out. This will enable us to write VT as a sum of the best linear forecast of VT using past incomes and the forecast error. So VT is equal to A0 YT minus alpha plus A1 YT minus 1 minus alpha and so forth, and our error term epsilon. With the expected value of YT minus I minus alpha, epsilon equal to 0. That's the gun. We would then want to multiply through by each of the right-hand side variables, taking expectations, and solve the resulting equations for the coefficients, alpha I. However, we cannot use the method directly since the variance of V and Y are infinite. We don't want things with infinite variance. We want to calculate stuff with finite variance. So instead, we need to alter the problem so that we're projecting a stationary variable, that is a variable with finite variance, onto a set of stationary variables. So observe that VT is, the expected value of VT is equal to expected value of VT minus 1 plus the expected value of W. The expected value of W is 0, as we know, but we'll talk about that later. And no new information is obtained at T that will enable the individual to improve the forecast at VT minus 1. Made at VT minus 1. I'm sorry, made at period T minus 1. The information about VT minus 1 contained in YT was already available from YT minus 1 and previous values of Y. So, my VT minus 1 given at period T is equal to the expected value of VT minus 1 given at period VT minus 1. And that's the same as my expected value at T minus 1 for VT minus 2. So the expected value, therefore, is equal to that. The expected value of VT minus 2 at VT minus 1 plus the expected value of WT at T minus 1. And continuing in that fashion, I can keep going backwards, and I can conclude that the expected value of VT at period T is going to be the expected value of WT at period T, the expected value of WT minus 1 at period T minus 1, and so forth for all the W's. So information about WT minus I in period T minus I can be obtained from the change in income from period t minus I to period t minus I minus 1. However, the change in income also contains all previous shocks in W. And we need to purge WT minus I minus WT minus I minus 1, in other words, that shock, and or those past shocks, of the effect of the previous W shocks. Formally, we project WT against the current and previous changes in income to obtain the following. WT is equal to A0, WT minus 1, plus A1, WT minus 1 minus WT minus 2, and so on, and epsilon 2. So with our forecast errors, ET orthogonal to the right-hand side variables that we want, right? The expected value of ET is times YT minus I minus YT minus I minus 1 equals 0 for all i's greater than 0. Then note from the previous equation, 57 and 58, that the expected value of VT is going to be the sum, right, of AI times YT minus I minus YT minus I minus 1 from 0 to infinity plus all of those going back one period from that, and all of those going back to one period from that. Doing the summations. And that would equal AI YT minus I minus alpha minus the summation from 0 to infinity of AI YT minus I minus 1 minus alpha and so on. By the way, there's a typo in there. That next one should be YT minus I minus 2 and then YT minus I minus 3. But I think that typo is pretty obvious. So if we telescope the intermediate term, we find that the expected value of VT is simply equal to the summation from 0 to infinity of AI YT minus I minus alpha. In other words, I just take that first term and basically I make I 0. That's what I get, and then something there. So multiplying 58 through each of the right-hand side variables and taking the expectations to get the equation, which they call the normal equation, the expected value of YT minus I minus YT minus I minus 1 WT is equal to the summation of AJ, where J is from 0 to infinity, epsilon YT minus J minus YT minus J minus 1 times YT minus I minus YT minus I minus 1 for all I. So to evaluate the expectations in 62, I get YT minus I minus YT minus I minus 1 is equaling to WT minus I plus UT minus I minus UT minus I minus 1. Right? So that the expected value of WT times what we were talking about before, WT minus I plus UT minus I minus UT minus I minus 1 is going to equal the variance of W, or sigma squared W, for I equaling 0, and it's going to equal 0 for everything else. You're not going to have any variance in that. You have 0 variance in the W's from then on. While the expected value of YT minus J minus YT minus J minus 1 times YT minus I times YT minus I minus 1 is equal to the following: WT minus J plus UT minus J minus UT minus J minus 1. And as you can see, the next one is simply substituting the J's with the I's, taking that, and therefore we get the following: if I equals J, right, that expected value is going to equal sigma squared W plus 2 sigma squared U. If the absolute value of I minus J is equal to 1, in other words, it's just one, if they're just one period away, then it's just equal to sigma squared U, or negative sigma squared U, and anything else is equal to 0. So basically what we're saying is if the variances are close in two time periods, or if the two time periods are close, you might have some positive variances. But as you move away, variance goes to zero. So I substitute the expressions into the normal equation we had before to find for I equals 0 sigma squared, which we're doing that. And remember, sigma squared here. That's going to equal A0 plus sigma squared W plus 2 sigma squared U minus A1 sigma squared U. For I greater than 1, I get 0 is equal to negative sigma squared U times I minus 1 plus sigma squared W times 2 sigma squared U AI plus sigma squared U AI plus 1. So that equation is a second order difference equation for the coefficients of AI, and by the way, that I should be a subscript. So I rewrite the second order difference equation as 0, AI minus 1 minus sigma squared W over 2 sigma squared U divided by sigma squared U, time, all of that times AI plus 1. With the corresponding complementary equation, again, don't worry about the roots. I get 0 equal to 1 minus sigma squared W over 2 sigma squared U over sigma squared U times lambda plus lambda squared. Basically taking those i's and making them roots. So our quadratic has the following root. 1/2 sigma squared W plus 2 sigma squared U over sigma squared U plus or minus the square root of sigma squared W plus 2 sigma squared U over sigma squared U quantity squared minus 4. So the discriminant is positive, so both roots are real, again. Also, we may write the quadratic as we did before, 1 minus k lambda plus lambda squared for any k greater than 0. We're going to go through the same exercise as we did before. If the root is negative, 1 plus k lambda plus lambda squared is positive, so both roots have to be positive. Finally, since the coefficient of sigma squared is 1 and the constant term is 1, the products of the two roots is 1. Therefore, we may write the two roots as lambda and 1 minus lambda, where lambda is less than 1. So lambda is equal to 1 plus r. Again, remember r is simply the ratio of the variances, W and U. So it's 1 plus r over 2 minus the square root of r, 1 plus r over 4. Well, as I said, r is the ratio of the variances of W and U. So the graph of lambda as a function of the ratio of the variances of W to the variance of U is as follows. In other words, as r gets bigger, lambda decreases, or vice versa. As lambda decreases, r gets bigger. So solution to the second order difference equation, AI is equal to A, just like before, lambda I plus B lambda 1 over lambda to the I power for two constants A and B. So now if B is not equal to 0, income for further into the past will have a bigger influence in determining the current expected value of permanent shocks. In effect, we again have to appeal to a transversality condition. The relative minimization here is that the minimization of the square forecast errors to give us a second boundary conditioning forcing B equals 0, and we can conclude that AI equals A lambda I. And that assumption is kind of, in other words, what a caveman did 2 million years ago doesn't really affect us too much today, at least as far as our consumption. Okay. So with A chosen as satisfying the boundary condition that I equals 0, sigma squared W is equal to A, sigma squared W plus 2 sigma squared U plus A squared U. Taking that and dividing that by sigma squared U, I get R, our ratio, is equal to A, R plus 2 plus A lambda, or A times 1 plus R over 2 plus R, the square root of R, 1 plus R over 4. And all of that's going to equal, all the R's go away, or solve for R, equal A over lambda, or A times 1 over lambda. So in this case, right, if I graph that as a function of the variance of W relative to the variance of U, R, right, as this thing increases, A increases, right, our our ratios of the variance also increase. So increases in the relative variance of permanent shocks decreases the effective lag income on current estimates of permanent income. Current income shocks will reveal the current value of W more accurately, making it less important to use lag income to filter out the noise of UT, or the noise UT. Right? So substituting that 74 into AI back into 61 way back then, or the expected value of VT, right, is equal to A, YT minus alpha, plus lambda YT minus 1 minus alpha plus lambda squared YT minus 2 minus alpha, and so forth. Using the lag operator for all those YTs and constant lambda and constant A, I get the expected value of VT is equal to A, 1 minus lambda times the lag operator, YT minus alpha. So basically all the information I need about V is in this period. So return our expression of 51 for the expected value of YT minus I for any I greater than 1. I have the expected value of YT minus I, I'm sorry, YT plus I is equal to A over 1 minus lambda L YT plus alpha 1 minus lambda minus A over 1 minus lambda. So I can substitute that into that last equation we had, into our equation for permanent income. So I get 1 minus beta YT plus alpha beta 1 minus lambda minus A over 1 minus lambda plus beta alpha over 1 minus lambda times the lag operator YT. Okay, questions? Like I said, I know that's daunting with the roots and stuff. Don't worry about the roots, just get the basic concept of what we're doing and what we're doing with different assumptions to get slightly different results. Empirical predictions of the theory. When the last equation is turned and substituted into a consumption function, the theory will imply that the consumption function of the form CT times the root lambda, CT minus 1 plus gamma 0 plus gamma 1 YT plus gamma 2 YT plus 1 plus UT plus lambda UT minus 1. Where gamma 0 is equal to alpha K beta 1 minus lambda minus A. Gamma 1 is equal to K, where K is a proportion, little k. 1 minus beta plus beta alpha, and gamma 2 negative K lambda 1 minus beta. In particular, you see that now we have an interpretation of the adaptive expectation coefficient on lag consumption. Lambda, it will depend on the relative variance of permanent to temporary shocks, U and W. We can think of that as U and W. Also observe that the coefficient of current income in the consumption function depends positively on A, and hence the ratio of permanent to temporary variance. The farmers that we had in our consumption function last lecture, right, have a higher component of temporary variation in income, so their gamma 1s are going to be smaller, as they found in Klein-Goldberger, right? So this is basically the same equation, except that we weren't using gammas, we were using other coefficients. Also observed that a econometrician looking at income and consumption data can estimate alpha and the variance of U and W from the income data. The expected value of Y is going to be alpha. The variance of YT minus 1 is simply going to be sigma squared W plus 2 sigma squared U. And the covariance, the difference between income between two periods and income in the previous two periods, right, is simply going to be negative sigma squared U. So if I can get the covariance for sigma squared U, I can get the covariance for sigma squared W. So equation 86 and 87 can be solved for the two variances. Then the consumption function can be estimated to obtain the estimated value for our root. In other words, we don't have to actually calculate the roots. We can do it here. Gamma 0, gamma 1, and gamma 2. If the theory is correct, these estimates of lambda and A should agree with the estimates based on the variances of W and U derived from the income data alone. So in other words, now we have a way to check it. The only new parameter in the formula for gamma 1, gamma 0, and gamma 2 are K and beta, so the parameters here are over-identified, giving us an additional test of the validity of the theory. And that's it. Okay, that's nothing, like I said, in the econometrics book. Questions? I really expected this lecture to take the whole 3 hours. It took 2 hours, an hour and a half. Okay. Questions? Okay, since there's no questions on this, let's talk about the rest of the class. We have one more lecture that comes on with it. I'd like to give another lecture on financial integration that won't be on the exam because just that. Stop the broadcast.